lifespan. Yesterday only gave a very good introduction for this purpose about the uncertainty of the involvement of the mitochondrial DNA, mitochondrial related factor in the mammalian lifespan. So I'm going to talk about why different species, mammalian species, have different lifespan. And this topic is very old, and the first one I know to talk about this was Aristotle, the father of biology. So let's start with the distribution of the mammalian lifespan. This is the total 1,008 is the total number of mammalian species we know the lifespan, and this is the distribution of the mammalian lifespan. It is close to log normal distribution. So, in the research, we asked whether the mitochondrial-related factors are associated with lifespan. Specifically, we regard three factors. Perhaps four: the mitochondrial DNA, the body temperature, which is related to uncoupling, metabolic rate, and waste production. So what is the difference of the mitochondrial versus the nuclear DNA? Everybody is talking about how much the mitochondrial DNA is more prone to damage, it's in close proximate to the oxidative phosphorylation chain. And one of the most striking structural differences between the nuclear and the mitochondrial DNA is the asymmetric distribution of bases among the two strands. As we know, in the nuclear DNA, the number of A, C, G, and T is equal between the two complement strands. And in the mitochondrial DNA, interesting phenomena that is that one strand is guanine rich, and the complement strand is cytosine rich, meaning that the distribution of bases among the two strands is not equal. So I'll start by showing you comparison of the simple calculation of base composition for this heavy strand with the lifespan. Okay, this is the hypothesis that the difference in base composition may reflect some damage that occurs to the DNA, and this is the result. As you can see, it's quite striking and very much unexpected, I would say, because even we didn't expect that high association between the mitochondrial DNA base composition for adenine, guanine, cytosine, and thymine, and the lifespan at the y-axis. So this was, we found it in 2006 and already presented it in the SENS conferences. Okay, let's go on. We think that it could be related to the lifespan because the most obvious difference between GC and the AT pairs is the number of hydrogen bonds. So more GC rich, I'll go back. The G and C, they both correlate positively with the lifespan, while the A and T correlate negatively with the lifespan. So the G and T, they both form 3 hydrogen bonds versus AT, which form 2 hydrogen bonds, and this could be important for example, thermodynamic stability of the DNA. So this is what happens in the heavy strand, which is G-rich. The cytosine cannot accumulate for some reason. This is the topology of the DNA. The accumulation of GC pairs lead to higher stability and longevity. From here, we will go on to the other factor, which is resting metabolic rate. It's known that resting metabolic rate correlates negatively with the lifespan of species. So we have 2 mitochondrial factors which correlate with the lifespan of species. Is there any correlation, association between these 2 factors? And this is I think the most, perhaps most striking finding of the study. that there is absolutely no association between the metabolic rate and the mitochondrial DNA-based composition, which are two parameters that correlate with lifespan, but not with each other. So what does this mean? This means that they could explain the lifespan independently of each other, and together they explain, well, I think it speaks for itself. It can explain more than 3/4 of the variation in the mammalian lifespan. As far as I know, this is the highest coefficient of correlation ever reported, because we found something new. Okay. One of the first observation, or perhaps a very promising strategy to change the lifespan of species, is changing the temperature. In exotherms, it is known that the lifespan varies as a function of the ambient temperature and as a result of the body temperature. As you can see, this is the maximum lifespan, and the mean lifespan is a function of incubation temperature in Drosophila, an exothermic species. And what about mammals? Are there any evidence for the effect of temperature in mammals? Speaking shortly, we found association between the mitochondrial DNA GC content and the body temperature. This here I show you the average values for orders, because different orders in our sample have different number of species. To avoid any bias, I show you the average values for body temperature and the GC content in mammalian orders. And here are the avian orders, the only other taxonomic group that is warm-blooded. Okay. We have two factors, the body temperature and GC, and we've seen, we can tell you by eye that species with low body temperature and high GC, they live much longer than species of comparable body size. And as example, I give you the naked mole rat. It is lots of time it's mentioned in the literature, but it's exceptionally long-lived, especially compared to similarly sized mouse. This is the allometric relation of the body mass and lifespan in the order Rodentia. You can see the naked mole rat where it stands, where it lies in the graph. And with regard to the GC content of the naked mole rat, is it exceptional? Well, absolutely not. You can see it at this red spot exactly on the regression line. I just want to show. This, of course, strengthens the relationship of the GC and the lifespan. And now, because I have very much little time, I get right to the end. Why does the metabolic rate relate to lifespan? Well, the issue of metabolic rate and lifespan is very old. It starts 100 years ago, actually. And by then, more data have accumulated about the relationship between metabolic rate and body mass and now also lifespan. What you see here is the relationship of not only basal metabolic rate, but also of the maximum metabolic rate. This has been published by Bishop based on the very much more accurate data. You can see that the slopes for maximum metabolic rate and basal metabolic rates are different as the body mass increases. And actually, this is called metabolic scope, meaning how much a species can increase its metabolism in proportion to the basal state. And it increases with body mass. And could this, well, we know that in many species, including human, the difference between old men and young men are the maximal capacities. There is a progressive decline in the maximum ability to expend energy, to run, to perform everyday, finally to perform everyday life. So note that the exponent of the regression for the relationship between body mass and the metabolic scope is 0.15. This is found by Bishop, and this same exponent is on the body mass is actually in the range of linear relationship between body mass and the maximum lifespan. So when you take body mass and you put it in this exponent, it will correlate linearly with the lifespan. So from here we get to the summary of this research. We can combine the parameters of body mass, the mitochondrial DNA, and body temperature to predict the mammalian lifespan with a very, very high accuracy. This here I show you for maximum lifespan. This is not load transformed. And therefore, what you can see it's very nicely, but the statistics is actually shouldn't be done this way. It should be the y-axis should be load transformed as well as the x-axis, and this is how it looks like. And that is to in summary of the study. I'll show this model of two pathways that determine the lifespan. One pathway is associated with the metabolic pathway, with presumably the metabolic stability, metabolic scope. And the other pathway is the mitochondrial DNA pathway. There is also a place for body temperature, which interacts with both pathways, and also has its own effect on longevity. And I want to thank to my lab members who contributed a lot to this work, and of course to my professors and PhD advisor, Professor David Freifeld, our collaborator Marina Bolson, and of course Hajik Moradian. And that's it.
Yes.